看是 reviewer 哪一台用这张键。都请那个检视好电脑是 OK 的。因为那个礼拜五的时候，大家比较不熟，比较会出问题。不过昨天还是有同学时间到了，然后还是PowerPoint的出不来，啊，所以麻烦大家检视一下。麻烦先把电脑接起来，投影出来检视 OK。好，现在是接在谁的？对，我这一台是接在你们，还是接在哪？
现在是这个，
在你们。好 ，OK， 可以了。所以这边 appointment OK 了。然后，那 reviewer 你们麻烦也接一下，然后请那个请助教这边帮忙切换一下，让 reviewer
直接接就可以了。
哦，直接接就可以了。
直接接就有信号了。
好，来，我们就直接接就有信号了，你就上来了吗？很好。开会时间，timer 一开始就一直算下去了。好，你们的 OK 吗？Yeah， so 非常好。So, okay, it's the time. So, good morning, everybody. Welcome to this session. So, at first, I would like to introduce the viewers. I am Cai Zhishen from 师大。
I'm Li from National Council University.
So I'm Guo Jialin from National Central University.
My name is Nan Fuguo from 中正大学。
So the team leader, please introduce your team member.
Hello everyone, we're Team Mingdao Mei. I'm from Mingdao High School. This is really cool. Jory Kao, Derek Wu, Emily Lin, and I'm Robert Lin.
So the opponent.
Hello everyone, we are No Riders from Taipei American School. I'm the captain, Darren Z. Here we have Ethan Hu, Billy Lim, Ethan Cho, and Kenneth Mo.
Okay, reviewer.
Hello everyone, we are Newgate from KGHS, and my name is Evangeline Yan. This is Jenna Du, Peggy Wang, Maggie Liu, and Olga Tsai. Nice to meet you.
Okay. So let's start the first part. The reporter, please challenge the question. Opponent, please challenge the reporter. Yeah.
We would like to challenge number 5, whistling mesh.
Number 5. Number 5, whispering mesh.
We reject the challenge.
Reject. Number 5, reject. So.
We challenge the reporter to number 3, siren disc.
Problem number 3. Number 3. Siren.
we also have a challenge.
So, accept the problem number 3. The reporter, please write down the name.
Oh, I'm so sorry.
For the presenter.这边会有什么转接头吗？
不需要什么转接头，他们没有就一样一些。
So, esteemed judges and fellow debaters, my name is Jerry Gao, and this is my question siren. And the problem statement is, if you direct an air flux onto a rotating disc with holes, a sound may be heard. Explain this phenomenon and investigate how the sound characteristics depend on relevant parameters. And our main focus would be relation between rotating speed and frequency, the relation between quantities of holes and frequency, and also the relation between different distance from the center and frequency. Now this is our demonstration video. Not here. That's just a photo of how we demonstrated. Yeah. And these are our equipment. Like we drilled holes into CD discs and to provide holes, and we use the air duster to provide a airflow, and the motor for a fixed spinning speed. And our first step, we first place the disc onto a holder, and then we connect the holder to the motor, and then we place the air duster near the holes of the disc, and we turn the speed controller on, and then we observe and record the sound and other. Okay, so this is our experiment setup. These lines are just to make sure that every angle is approximately the same. Okay. So why does this phenomenon happen? So it's because the airflow is somewhat close to the sound frequency, which is somewhat close to the omega, which is how many rounds I spin in 1 second times the holes of quantity, the quantity of holes. And the phenomenon explanation is that once the airflow passes through the air, the hole, then it will push the CD less. And when it moves over here and it doesn't pass through the hole, then it will push the CD more. So then it will have a fixed like push and not push, push and not push, which makes the CD vibrate. And the vibration of the CD will cause the air to vibrate and create a frequency of sound. And so we use a application that use the Fourier transformation, so we can see every single frequency and how big it is. And in most of our experiments, we can see that there are 2 peaks, and the other may be other sounds that we do not want to investigate. And these are the sounds that we want to focus on, and these are the 2 main characteristics that we want to focus. So experiment 1 will be the relation between rotating speed and frequency. Now we change the rotating speed, and we want to see what would happen when we change rotating speed. And then this will be the first peak, and this will be the second peak. And then we found that the first peak, that was a typo. This is the first peak, and then the error percentage of slope is like that. And then there are actually, you can see that it's actually very close to the line, like our theoretical line. So the trend between the CO value and the second peak is actually first peak is actually very similar. And the slope of the second peak is, first peak is similar to the theoretical value. And the error percentage of the slope is 9.83, which is a little bit big, but that would be the errors we want to discuss later. And the second peak and theo value is about the theo value divided by first peak. We'll discuss that later. And so in our second experiment, we changed the number of holes. Change the number of holes, but we fixed the rotating speed. So we think that the frequency, since in our hypothesis, we think that the frequency will be equal to the quantity times holes of holes times omega. So if our holes numbers increases, our frequency will also increase. Yes, so this is like mostly this is the rotating speed, and this is different holes. Yeah, 12 holes, and 16 holes, and 34 holes, 32 holes, and when we add it back like in one graph, and we see that whenever the hole, when we have more holes, then the frequency gets higher, which is the same as what we thought would happen. Now, when there is like the higher rotating speed, then there will be less error, and we also discussed that later. So this explains that the quantity of holes will be proportional to the rotating speed, and the slope is proportional to the zero value, which makes we think that our hypothesis might be quite correct. So our third experiment was that we changed different like radius from the center, and so this is 16 holes, 3 cm from the center. This is 4 cm from the center, and 5 cm from the center. And we see that at different conditions, the trend of the second peak and the first peak is similar. So if our hypothesis was correct, that means when the omega is fixed, the radius will not affect our experiment, which makes us keep thinking that our hypothesis is definitely correct. So now we want to accept the intercept. So when the rotating speed is 0, we might actually see in our theory that it will be 0, because the quantity of holes times 0 is of course 0. But when we tested it, it's not 0. So we want to explain why isn't it 0. So we added something, another theory called the natural frequency, and so the error might be caused by the natural frequency. So we want to put that back into analysis. So our hypothesis was that the wave function is x of t is a sine omega t. So it will have a long waveform. This was the waveform that we originally supposed. And then after correcting it, then we formula like this, and we heard it's because that when omega is 0, then what we hear, the frequency we hear is actually the natural frequency of the CD. So now the natural frequency, when the disk is like rotating very fast, then it hits really fast. So it creates new sound wave of the TRT, and the natural frequency adds up and becomes striking frequency. And this is how we corrected our first formula, like our hypothesis. And when we corrected our theory, then it actually, the first peak actually mostly fits our theoretical value, which makes we think that our experiment is correct. It highly fits, like the error percentage is even very, very, very low. Yeah. So there will be a positive correlation between the rotating speed and frequency, and there will be a positive correlation between quantity of poles and frequency, and uncorrelation between distance towards the center and frequency. And under high rotating speed, the experiment value is very closer to the theoretical value, and then the second peak value is the first peak value fits better to the theoretical value. And the prediction of our, so we think that our prediction was correct. So now we want to talk about the errors. We can see that the slope of the second peak of the value is almost always the 2 times, like the slope is almost always 2 times of the our theoretical value. And why is that? And why does that happen? We think that when the airflow hits the disk, not only does it vibrates, it also has another like air dense and not dense. So it's like this. This is the airflow, and then this is the disk, and the hole. And whenever, like when the airflow over here, like airflow hits here, then there will be like, this will be dense, right? And this will be not dense because it goes through the hole. So it will be less dense. And then when it comes here, then it will be dense again. So it will fit our theory, fit the 2 times efficiency. So because one hole actually creates 2 like dense and not dense things. So it fits the second peak, it fits our theory too. And then the other thing that we think is why does the error become smaller when the rotating speed is faster? Is because the disk wobbles, does not like vibrate that much. So the error will be smaller, and that will be the end of our presentation.
Okay. So the opponent will test the question.
Okay, so first of all, were you able to control the airspeed, or was your airspeed just constant?
It's fixed.
Okay, so how did you record your sound? Was it MP3 or WAV?
It was just phone.
Huh? Yeah. So what type of file is it?
What type of file?
Okay. It doesn't matter. So how did you observe the vibration of the CD?
This is our theory. Like when you pass through one hole.
Okay,
then,
thank you. Can you move to slide 15?
okay.
Wait, so what do you mean by the first peak and the second peak?
This is the first peak. And
So
then the second peak.
wait, okay. Did you consider air turbulence in your experiment?
What's air turbulence?
So okay, we'll talk about that later. So you didn't consider anything about like Reynolds number or Struble number then?
No.
No. Okay. So then, do you know vortex shedding? What vortex shedding is? Or vortices? Okay.
We can explain that later.
Okay. So, can you explain your natural frequency value that you added on?
The natural frequency is the sound that we heard when we blow the disk when it's not rotating.
Okay. So then, did you consider the size and shape of the holes?
We made it like mostly like the same.
So
shape.
all the same size.
Yeah.
Okay. So did you consider the amplitude of the wave that you saw? So you have different waves, right? Did you consider the amplitude?
You mean in our second peak picture?
So the frequency. Did you have a frequency graph?
Like in the
Okay, time is up.
Okay.
Hi, I'm Darren D from Gnome and I will be the opponent for Sire. So the problem statement says if you direct an airflow onto a rotating disc with holes, a sound may be heard. Explain this phenomenon and investigate how the sound characteristics depend on a relevant parameter. So what I believe should be the main focuses in this topic is sound, vortices, and many parameters. So in his observation, he had the audio clip of he had a clip of the experiment shown, but the clip was unclear, and he assumed certain parameters are constant, and his setup was not very good for this experiment. So for the theory, he had a quantitative theory for the frequency, which is good, but his qualitative theory was very unclear when he was explaining, and he did not look into many variables, and he did not consider enough relevant parameters to the topic statement, and he did not consider vortex shedding or turbulence, and then he did not consider Reynolds number and Strouhal number, which I believe are really important to this topic. So for the experiments, he did have some relevant parameters that were considered. He did change the number and speed of the disc, the number of holes and the speed of the disc, but he did not experiment with the size of the holes of the disc, as well as the shape of the holes are not experimented. And he had a lack of graph of the wave in his presentation. So in his data analysis, he did analyze the error to a slight extent, and he did have a theory fitting and a best fit line, but he did not have error bars on his graph, and he had little error analysis. So for the discussion, I would like to talk with the reporter about their understanding of sound and frequency, which is like the compression of air, as well as their quantitative and qualitative theory. And because the opponent did not mention about vortices, vortex shedding, or turbulence, I would like to go over that with the reporter, and how Reynolds number and Strouhal number are affecting the vortex shedding and turbulence. And for the experiments and parameters, we would like to talk about their setup errors, possible setup errors, as well as the accuracy of the microphone. And so the size of and the shape of the hole may affect the sound characteristics produced, as well as the speed of the airflow, which they did not consider, and as well as the material of the disc, which may also create a different sound. And so they did not have error bars in their graph, so we do not know actually how much error the frequency had. And for data analysis and conclusion, we want to make a comparison of the different parameters and their effect on data, but they did not consider enough parameters, so I believe we can go into that. And for their data, and then they had little error analysis, and then they did not explain vortex shedding or turbulence, so that's a big topic I would like to go over. Okay, I would like to go into my discussion. Okay, so can you explain to me the phenomenon again? Because the explanation you gave was very unclear.
You mean the first peak or second peak?
The first peak, the fundamental frequency.
It's because when our airflow is actually quite big, so when you blow the air, and it's like when you blow the disc and it goes through the hole, then it will the force that it is receiving is less, and when it's not over the hole, then the force it's receiving is higher, so it would start to like
Okay, I slightly disagree with the reporter, because I believe that the frequency you hear is given when the disc is spinning. There are airs that's going through, which and it changes the pressure of the air. And when the disc spins, it stops. So then you have regular pressures of air going through the disc, and that's what is creating the frequency. Because sound is a pressure wave. So I do not believe that you explained that very well. Okay. Now we can go into the vortices and vortex shedding. So let's come to the board over here. So do you have any idea what a vortice is or a vortex is?
you mean like flowing
Yeah.
air?
So yeah. So basically, what happens in an experiment is, let's say this is the hole, right? So basically, we have like, because your experiment is done vertically, I'll draw it like this. So when there's air going through, the air should just go through, right? But then because of Bernoulli's principle, where this part of the air is this part of the air has high velocity, so then it reflects that the high velocity part has a low pressure, while
Can you explain what the blah blah principle is?
Bernoulli's principle.
Yeah.
So basically what happens, let's say you have an airplane, right? And so there is a lot of, you know? Okay, so there's low pressure here, and because the velocity of air here is high, or is low, so the pressure here is high. So what happens to this is since the pressure here is high, it pushes on the low pressure part, which creates a vortex, right? But if you think about it, the air will only go like this. But because of viscous force, which is similar to like the air resistance in the air, the air will start to curl, and this can create some sound. So did you consider that in your experiment?
We believe, even though there might be sound, but that would be irrelevant to the 2 peaks that we want to consider.
Okay, so I still believe that you should consider this.
Yeah, it might be right
plus
here or
vortex.
something, but we want to investigate 2 major characteristics, which is these 2 peaks.
Right, but the sound you are collecting is because the air is going through.
Well, then we have different ways of thinking this question. Yeah, how can you prove that is wrong?
Would you like to explain? Would you like to explain why this wouldn't affect your experiment?
It might affect, but that, I mean, it might be over here or something. It might not be these 2 peaks. Then can you explain why this must be these 2 peaks?
No, so I'm just saying that these are the frequencies. The frequencies you're hearing is because there's air going through, right? And then so when it stops, there's this covers the air for a second, and then it lets air go through again, and that's what's creating the sound, right?
I mean, the compression of air.
The compression of air, yeah, and the regular So, but then these airs, they're going through like this. This is the motion. So this might affect how the sound is created, and so I think that you should look into that.
Okay.
Okay, and so I also believe that you did not look into turbulence, right? So did you have a FFT graph? Yeah, so you only had a wave, right? Can I see your wave graph or in your presentation? Okay, so I don't get why you looked into these 2 peaks but did not look into like some other peaks, like that one. Can you explain why you chose these 2 peaks?
Okay, so these two peaks, I can't show you right now, but they are the most steady ones, and these they go up and down, up and down, up and down. So we believe it might be the sound of the motor or the sound of other things.
Wait, so when you recorded this, you had your disc spinning constantly, right? And you recorded it over a time period.
Yeah.
So should the wave not be similar in a similar fashion? Why is it just? It looks to me like a random wave, right?
This is not
This
one
is
wave.
not-
This is like this is the frequency. This is the frequency level. This is because of Fourier transformation. So
Right.
this is
So you talked about Fourier transform, right? So this is the wave this is the frequency graph that you get after Fourier transform.
yeah.
Okay. So then, what are the axes of this wave graph? What are the axes? What's the x-axis and what's the y-axis?
So x is like the frequency, and this is like how big the depth is.
Is this the amplitude of the wave?
Decibel.
Decibel?
Decibel.
So the intensity of the wave, right?
Yeah.
So then, why would you not look at this peak? This peak has a higher decibel than these 2, right? So shouldn't you consider this frequency?
Because this is not steady. This frequency might be caused by like
And
human
if you look at this
speaking.
graph, you can see that this frequency here, and then there's multiple peaks in frequency, and they look like harmonics, right? They look like multiples of each other, so they should be harmonic. So shouldn't you be looking into this in your experiment?
Want to correct my saying. This is the motor sound. This is the motor frequency. We tested a frequency of the motor, and this one is the frequency of the motor.
So this is a frequency you got
Of the motor.
sound. Of the motor. Then what about this one?
You mean this?
What about this graph? So this graph and this graph is different, right?
Oh. This is when we blow the air. This is when we blow the disc, and this is when we blow the disc, and this is when we don't blow the disc. Like
So then, this is not a frequency graph?
this is a frequency graph, but
Is it the
these two are
frequency of-
irrelevant. These two are
Okay, so then
irrelevant.
which one is the one that you see for the frequency of the sound created? This one, right?
Yeah.
Yeah, so what am I telling you? I'm telling you that there's a pattern here, but you're not investigating this, and you're investigating this?
Why can't I investigate those?
Sure, but then you should investigate these as well, because you're seeing a pattern there. And so obviously in a sound characteristic, there's for something, everything has a sound characteristic, and the sound characteristic is defined by however many by their characteristics of the harmonics. And so
Wait.
what I see here is that you have a frequency here and then you have harmonics here.
We know that there are harmonics, but these might be the harmonics of the frequency that the motor creates. Because whenever we change the frequency, these peaks will not change.
Frequency of the motor?
The rotating speed. When we change the frequency of the rotating speed, only these two peaks changes. So the peaks at the over there would never change. Like these major peaks will not change.
But aren't you? Okay, so then this is the frequency, and then that's the amplitude. So how fast are you spinning your disc, and how many holes do you have on it?
We have on our graphs. This is the rotating speed, and then this is the frequency.
So how many holes do you have? 16.
And this is the theoretical value, like what we wrote before.
Alright, so so I don't think you consider turbulence in your experiment, right? So let's talk about turbulence, because this may also affect your sound. So turbulence is just chaotic movements in air that create that. So when the direction of the air and the speed of the air is different. So this turbulence is given by Reynolds number. So Reynolds number is equal to the density times the velocity of the airspeed times the diameter of your hole over the viscosity of your experiment. So this is a turbulence. So you should have I think that you should consider all of these values into your experiment, because
Why are you trying to fit your theory into my experiment?
no, because your experiment, I believe that this is just a suggestion. I think that you should investigate more, because your theory only has the speed of the disk as well as the number of the holes, and that only gives a frequency. But if you look at the problem statement, it says to investigate the sound characteristics. The sound characteristics is not only the frequency. You have to look into other things like the amplitude of the sound and also the harmonics of the sound. But you did not consider that in your experiment. So I'm giving you suggestions of what you should do. So you did not look into turbulence. You did not look into like
the time is up. Please summarize your discussion.
okay, so first of all, we talked about how we talked about the theory, and I tried to get the reporter to explain their theory qualitatively, and I felt like the explanation they gave was unclear, and I had to re-explain it to them in terms of how sound is formed, and like the pressure waves of a sound, and how there's like regular the air is getting blocked and going through. And so we also talked about Bernoulli's principle, as the reporter did not understand, or the reporter knew about the Bernoulli's principle but did not know about the vortices.
Yes, but no, he came back later, so I added a little bit, meaning seconds. So please keep going on.
Oh. Okay,
Still
so
have 10
we also discussed about the first two peaks of the graph, and the graph was very unclear, so I had to keep asking the reporter what it is. And I believe that the reporter should look into the different frequencies after the first one. And we also,
Yeah. So, the reviewer, please start your question. 待会让他站回来开始再
So first reporter, what do you think are the most important parameters in this experiment?
The frequency of the sound. Oh, the whole quantities and the spinning speed.
so I believe that since the plot statement is asking about the sound characteristics, there are many parameters that should be considered, including the size of the holes or the airflow speed, which may affect the turbulence, but he did not go into that.
So you discussed about the motor sounds. So do you think if you were to remove the motor sounds from your data when you were recording the sounds of the phenomenon?
It's because we don't have the kind of application, and when we try to use the cancel sound like in the iPhone app, then it cancels like most of everything. So we think that never mind, we just investigate first.
Yeah, I feel like you should try your best to remove all the extra frequencies, because I cannot tell which frequency was actually relevant to this experiment. If you have a motor frequency that's larger than the actual frequency, then I think there's something wrong with your data.
Then what would you suggest them to do if they were to, like, what?
Right, of course, they talk about the canceling of the frequency. I feel like they should try multiple ways of doing it. I believe they only tried one way because they looked into the application and it didn't work. But there are many applications that they didn't try. And if you look at the frequency, so that frequency on the top, that has to be some important frequency of the experiment, because it's larger than the actual frequency heard. So there's something wrong with that.
So to the reporter, did you repeat this test several times?
I mean, yeah, we did.
And was every single time?
These peaks were always the same, but these two peaks would move. I mean, in one condition, or
Yes, under one condition.
under one condition, these two are the steadiest, the most steady peak.
So under one condition, how many times did you repeat each experiment?
5 times.
Wait, can I say something? So under one condition, when the disk is spinning at the same speed and there's the same number of holes, then obviously the frequencies would not change. Like if you change the speed at which the disk is spinning.
I was trying to explain that what would change, but later I got that was a misunderstanding of the reviewer's question.
Okay.
So opponent, what do you think about the 2 peaks in your experiment?
What do you mean by what do I think about the 2 peaks?
Do you think that what causes these 2 peaks to be?
It's possibly the actual frequency of the disk, the one that the disk creates, but we cannot be sure because of the extra noises in the room, which are larger than the sound
Time
here.
is up.
Thank you.
Yeah.
I'm not saying serious. I did explain that.
Yeah, but it's just like sometimes it feels like it too. It's okay. It's cool.
the reviewer reads the flow.
So I'm the reviewer for problem number 3, siren, and I'm from the team Newgate. So the problem statement is that if you direct an airflow onto a rotating disc, a sound may be heard, and we have to explain the phenomenon and investigate how the sound characteristics depend on the building parameters. The reporter stated that the theory was the sound was created because of the vibrating of the CD. And their experimental factors were the rotating speed, the quantities of the holes, and the radius. The conclusion of their report is that the more high speeds in rotating causes higher frequency. There's a positive correlation between the quantities of the holes and the frequency. And the distance from the center did not affect the frequency. And in their high rotating speed, their experimental value of the second peak is closer to the theoretical value. The reporter had a lot of statistics. They showed graphs, and in their graphs there were actually error bars, which the opponents missed on this. And they did calculate their error percentages. Their experiment bars matched their theory, and they showed videos of their experiment. But the reporter did not consider many parameters that could have been crucial in this part. The opponent took notice of various parameters and asked a lot of questions according to these parameters. But there were some mistakes in regarding the reporter's presentation. In their discussion, they asked, did you control your airflow speed? They said it was fixed. Did you consider Reynolds number? They said no. And they asked to explain the natural frequency value. So the sound, they explained that the natural frequency value is the sound heard when the disc was not rotating. Did you consider the size and shape of the holes? And they said they were all the same. Here to explain the phenomenon again, the reporter said that when the airflow goes through the hole, the disc receives more energy. The opponent says that it was because of the change of the air pressure, it was making sounds. And we would agree with the opponent on this part. Because of the velocity near the disc is low, the higher pressure airflow pushes it and can create sound. And the reporter believes that it doesn't have to do with the two peaks. And we think that this might need some more investigating. Why didn't they choose the other peaks? Their reply was that it was more unstable and might be the motor. But we think that if these were turned into decibels, the decibels were turned into energy and subtracted. The remaining energy will only be the sound created from this phenomenon and could be observed even more. They didn't consider the turbulence, and we believe, like the opponent said, that they should consider this. What do you think the most important parameters are? And this is a question I asked. The reporter said the number of the holes and the rotating speed, while the opponent said that there were more parameters to consider. How will they get rid of the background sound? The reporter stated that the application did not have so, and the opponent said that they should have tried more ways. And as I said, we could turn them into energy and turn it back. Did you run their test several times? 5, and I think this is a good time for them to run their test. What do you think about two peaks? They said they were most stable, and the opponent said they cannot be sure since there are other peaks, and it might be generated by a phenomenon. And we agree with the opponent.
Time
Thank
is
you.
up. So the concluding remark.
We did put the error bars in our presentation, and we actually conducted 5 times of the experiments in experiment. And since our experiment fits our data well, so we think that our theory might be correct. That's why we didn't consider the Reynolds number on the impact of the air turbulence. The air turbulence might have the effect, but it will not change the it might change the sound waves, but it will not change the frequency. And then we have talked about the Fourier transformation. The reason why we only discussed the stable two peaks And since the harmonics shown is the Saki frequency of the motor, which we tried to eliminate, but we had no way to make it well cancelled. And so we would keep working on investigating other characteristics in the future, but that would not change the frequency that we want to mainly discuss about in this phenomenon. Thank you.
Okay. So, the question from the viewers. So,
I have a question for the opponent. You gave me the impression that you believe that turbulence or vortex are very important in this experiment. Am I correct?
Yes.
Then how would you expand the two peaks observed by the reporter? Can you use your argument about turbulence or vortex to expand the two peaks?
So I don't believe, so actually when I looked at their data, I was very confused because.
So you think the data is incorrect?
No, I believe that they should have looked into the other.
Yeah, I understand it. Why there are two peaks if you want to use your argument to explain?
Well, I mean,
If you think the data is correct, then
I think it's,
you think turbulence is important, then how would you explain?
explain turbulence.
No, the two peaks using your argument about regarding turbulence.
No, I believe that the turbulence can affect the sound. I'm not saying that it'll affect the main frequency, the fundamental frequency.
When we do experiment, we have a lot of variables.
Right.
And we have to pick the important ones. And those minor ones, if they are not that important, then we probably first we ignore them. Then later we can add some to your field.
Oh.
Not
Yes.
keep pricing on the minor ones first.
Okay, please keep the question
Okay.
as simple as
Okay,
possible.
can I explain why I looked at the multiple frequencies? The other frequencies?
Yeah, sure. Show the reply, and then we
Okay,
move to the next
so-
question.
Their graph was about the intensity of the sound. So if the intensity of the other frequencies are larger, then I believe that we should look into those ones because there's something, those should be more important. There's more prominent in our.
Okay, thank you.
Yeah.
So maybe next question.
How do you order? I have a question for you. How do you explain the second peak?
Second peak
Yes.
is
Why is there a second peak?
is because when the airflow is passing through this part of the hole, then it will create one frequency, one like compressed and not compressed. So there will be one here, and then when the disc turns and it becomes like this here, there will be another one. So it's like about 2 times the slope. So we believe this might be correct.
Okay. So,
Do you believe so with the reviewer?
I think there's, since their experiment results fitted, if you think that this is probably correct.
okay, some other question?
The opponent say that the S501 maybe the format maybe
Yeah.
affect the data you record.
Yeah.
Okay, so what's your opinion or all of you?
So I'm not too sure about why this happens, but when, let's say you're using an MP3 player, the MP3 player actually misses some of the sounds that are generated in the real world.
We got, since this is a comparison, like, if we use the same file format throughout our experiment, it won't affect the results of our comparison.
We believe that different formats, like file formats, might like as the opponent says, but that wouldn't change what we want to mainly investigate about.
Okay. So, is there any other question? Yeah, so let's go. So finish. Okay. So everybody ready? Yeah, one moment. The scoring is okay. For reporter. No, I mean for everyone. Yeah, okay. So for the reporter, the score is 76566. For the review, for the opponent. Yeah, so it's really different. So the score is 87764. Okay, so for the reviewer, the score is 87677. So is there jury want to add some comment? Maybe Professor Man.
Okay.
Yeah, you give a
Yes. The
relatively
reason why I
lower,
gave
yeah.
it 4 is because when you discuss a problem, you first focus on the key point, not the minor point. After you consider the key point, and I believe their model or their theory explains their observation correctly, then you can go on to the minor point. You're not just going to the minor point and keep emphasizing on the minor point, and that's not the way we do physics.
Okay. So is there any comment?
I think the opponent may want to keep some secret from the contribution of the currents.
Okay. Yeah. So yeah. 所以那个我想换回中文啊，我讲。Okay, so let's start the next stage of the tournament. So the opponent, please start to challenge your question.
We challenge problem 12, rice kettlebell.
Question 12, rice kettlebell.
We reject the challenge.
Reject.
We challenge problem 9, oscillating screw.
Problem number 9, oscillating screw.
We accept the challenge.
So accept problem number 9. oscillating screw. So please write down the name of the presenter. Okay, please start.
Hi, my name is Ethan Hu from Team No Nighters. I'll be reporting on problem number 9, oscillating screw. So in the problem statement, it states, when placed on its side on a ramp and released, a screw may experience growing oscillations as it travels down the ramp. Investigate how the motion of the screw, as well as the growth of these oscillations, depend on the relevant parameters. In this report, my main focuses will be what affects the oscillation or growth of oscillation, and what parameters affect the motion of the screw. This is what I will be covering in the presentation. So, phenomenon investigation. This is our setup. In our setup, we set up a camera stand above a ramp, and then we elevated it using a rack. We calculated the incline angle by taking the height between the bottom of the ramp and the rack, and we were able to vary the type of ramp, the type of screw, and the incline angle through this setup. So here are some key observations we noticed in our initial trials. First of all, when the screw slid down the ramp, there would always be oscillation. Second of all, when the screw accelerated down the ramp, or there was an increase in the translational velocity going downwards, the oscillations grew. Third, when the screw started to stop, or in the cases where there were no growing oscillations, the screw experienced dampening harmonic motion and it would stop. And the final one is that when the screw would flip, there would be a break in the oscillations, and then it would continue on after a short gap. Here is a video of the phenomenon. So over here, these are some tracking graphs that we can use to demonstrate the second observation, that when the velocity increases, the angular velocity also increases. While the angular velocity is not very clean, you can see that whenever the velocity peaks, it corresponds to a similar peak in the angular velocity, representing growth and oscillations. And here is the video phenomenon of when the screw does not experience growing oscillations, in which it experiences dampening and stops. So, how would we describe the motion of the screw? To describe the motion of the screw, we use a cutoff cone. This is because the cone shares the similar characteristics to the screw, and there are two major contact points, with the radius of the outer layer of the cone corresponding to the head of the screw, and the radius of the inner layer of the cone corresponding to the tail of the screw. We understand that the inertia of the screw is not that similar to the inertia of the cone, which is why we will include relevant parameters to account for that in later observations, and that the contact area of the cone is different from that of the screw. We use a cone because, like I said, when the cone rolls, it has the different velocities to the outer inner diameters, which is similar to the way a screw rolls. If you would like to not understand it in terms of the cone, you can also understand it in terms of the differential steering of a car, in which case the two different velocities of the wheels correspond to a different arc. Another relevant description of the screw is that when the screw rolls, it rolls around a pivot point. By looking at, these are relevant lengths of this conal model of the screw that we think will be relevant to the oscillations of the screw motion. A couple of other relevant parameters we thought to mention would be the different angles we accounted for. So the two dependent angles, phi and theta, are the different ways we can measure the growth and oscillation, are ways we can measure the motion of the screw itself. So theta would be how we measure the growth and oscillations, or the arcing motion of the screw. We take the angle between the two different positions from the pivot point to the center of mass. For phi, this is basically the rolling motion of the screw. We do not track that in our experiment. However, we account for that in our calculations because it is more of a conversion variable. For delta, that's the angle of incline between the screw and the ramp, and gamma is the angle of incline of the ramp itself. So, before we start on to the theory, here are some parameters we took a look at in order to figure out what would be relevant to our theory. So first of all is the changes in the friction coefficient of the ramp. And then the second is using different types of screw. This allows us to change both the length and the mass of the screw. We understand that changing two different variables at once might not lead to the most proportional results, but we're not able to come up with a way in which we could vary the length of the screw without varying the mass, or the mass of the screw without varying the length. So if you take a look at these two graphs, this is the angle versus time, and this is the angular velocity time of two different types of boards, wood and cork. The wood we used had a higher coefficient of friction than cork, and we were able to see that the growth and oscillations of the
angle was greater when there was a higher friction coefficient. Second is type of screws. We did not include graphs as the shorter screw would typically do flips, while the longer screw would typically come to a stop due to dampening growth. But some observations we noticed when we were doing these types of screws was that with the length increase, there was an increase in the period of oscillation. Additionally, with the longer length, there was a higher chance of the screw stopping. And then with the smaller length, there's a higher chance of the screw flipping. So modeling. First of all, before we start our model, here are some assumptions. We assume that the slip occurs at a constant rate for the entire experiment, and we can calculate that with the constant beta and the conversion from the tangential velocity of the screw. As you can see from here, this tangential velocity is equivalent to beta r radius of this arc, omega theta, or the angular velocity. And then additionally, the only significant loss of energy is from friction, because that was the only dampening effect we observed. So, how do we explain the growth and oscillation of the screw? We explain it through the types of energy acting on the screw. So energy at a certain point in time is equal to the potential energy plus the kinetic energy of the translational action of the screw, the kinetic energy of the rotational action of the screw, and the kinetic energy of the pendulum-like action of the screw. Additionally, there's also the loss of energy due to work from friction. Essentially, when the screw falls, it converts from potential energy into kinetic energy, right? So, the reason why there's growth in these oscillations is that as the potential energy converts, it mainly converts into both rotational and pendulum kinetic energy, or the arcing motions. When it converts to the pendulum, there experiences a greater arc, or growth in oscillations, and when it converts to rolling, the rolling then transfers into a pendulum because there's a difference in velocities which contributes to the pendulum kinetic energy. So over here, this is how we model the inertia of the screw. We have the pendulum rotational energy. We have mr squared. However, we factor in cosine delta because the radius to the center of mass is different from the board. And then for the rolling along the axis, we were not sure how to factor in the small proportional constant, so we use epsilon for that. So total energy equations. Here we solved all the equations in terms of the angular velocity of the oscillation itself. And then over here, we solved for angular velocity. In order to track the experiments, we had to figure out what the radius from the pivot point to the center of mass was, because this is sort of like a pendulum motion or rotational kinetic energy. We did this by using this a system of equations where the total length from the tip to the pivot point was r, and it's equivalent to the radius from the pivot point to the tail plus the length of the screw. So basically, this corresponds to the length of the screw. Additionally, we can solve for the other version is that the circumference of the outside is proportional to the circumference of the inside, because as we know, the circumference of the outside is some multiple of the circumference of this because it's rolling into an arc. And then because the angular velocity is the same, or it's a rigid body, there's the same multiple over here, which is why we can do that proportion. Solving the system equations, we get this equation. And then in order to figure out where the pivot point is, we can use vector analysis to figure out the equation from here. If you would like, we can explain it later on in discussion. So experimentation and discussion. First, we figured out where the center of mass was, because the center of mass was different for each type of screw. For each trial, we would basically figure out where the center of mass was by hanging the screw along a string and then figure out where the balance point is, making sure it's level through a bevel, and then measuring the distance and then subtracting that from the outer radius. Here's some concepts for the different experiments we tried. Here's how we track the angular velocity. We essentially take the tail and the endpoints, and then we find the length from the pivot point, and then track the pivot point towards the kinetic and translational, and then track the angular velocity change in between different positions. When we solve for these constants for one certain experiment, this is for the wood bore on 1 inch, we're able to find a linear relationship. And then if we took the inertia calculations we had, we were able to calculate periods with about a 25% error. For this period calculation, we derive this from equating the two different types of torque, or the restoring force of gravity torque is equivalent to the torque of the rotating action or the kinetic energy of the pendulum itself. So analyzing error for both of these types of experiments. First, in the linear trend, this is a good point because it shows that there is the relationship that we described in the value. However, the slope was different because in the equation, we expected a one-to-one correlation between the square root of theta and also the equation over here. However, we can explain this by the fact that we used a ratio of 1-to-1 for the slope in this constant over here, which could explain why the slope of this graph is not 1-to-1. Additionally, the y-intercept is not 0. This is because the initial angular velocity is not accounted for in the theoretical model. And then the coefficient of velocity was 0. So over here, we explained that by saying that the translational kinetic energy had no effect on the growth and oscillation. And then there was an error of 25% for calculating for period. We believe this is because we did not factor in some degree of constant for the inertia, so we could probably explain that better. So to conclude, oscillations grow due to conversion of potential into rotational kinetic energy and pendulum kinetic energy when it slips. Despite the growing oscillation, motion can stop due to work done by friction, so there is a damping factor. We performed analysis how the length of the screw and the friction coefficient of the screw and ramp affected the motion of the screw. We predicted the period of oscillation with a 25% error, and we verified that our ancient equation through graphing the relationship between angular velocity squared and our equation, and the error between our ideal graph and the equivalent data show how much the slip occurs.
Okay, time is up. Yep, so the opponent asks the question.
Okay. So the first question is that you mentioned in your conclusion, you have 25% of error. Do you think that your statistics are reliable and considerable with a 25% error?
I believe that the 25% error can be explained through a miscalculation of the inertia, so I still believe the statistics are reliable.
Okay. So the second question is on page 19. So can you explain how the equations relate to your experiments?
Essentially, over here we included the equation for total energy. Then we solved it using the different inertia and energy calculation for translation of kinetic energy. So over here we sub that into this term, sub this into this term, and then solve for the different parameters we track in our experiment, such as the angular velocity, the length of the radius, and then the mass of the screw.
Okay, and so on page 20, so can you explain this equation and which parameters you have experimented?
We literally took this equation over here, took it down, solved for the angular velocity squared, and then we basically tried to track how the angular velocity would relate to this equation.
Preparation time. start.
So, hi, I'm the opponent from KGHS Newgate, Evangeline Yan, and today I'm discussing about the oscillating screw. So first is the problem statement. When placed on its side on the ramp and released, a screw may experience growing oscillations as it travels down the ramp. Investigate how the motion of the screw, as well as the growth of these oscillations, depend on the relevant parameters. And according to what I just heard from the reporter, their main focus is what affects oscillation and growth of oscillation. Also, what parameters affect motion of the screw. So the reporter simply talked about their theory, which is the potential and kinetic energy translation. And also their experimental factors are different ramp material, friction and coefficient, and also different type of screw, length and mass. So here are some pros and cons about the reporter. First, they had a clear presentation, and also they had a clear theory and equations. Also, their time management is very good. And here are some areas for improvement. First is that they could have more explanation of the graphs. Also, I didn't see error bars in their graph. Third, they should have more focus on their data of experiments. And these are the points that I would like to discuss with the reporter later, which are first about their errors, and second about their equations, third about the picture that I saw, which is their setup, and fourth is friction, a very important point in this experiment. And last are the parameters that they mainly focus. Okay, so can the reporter please? So first, can you open your setup picture? So the first question is, how big is the board?
This board over here is 1.12 meters.
1.2 meters.
1.12.
1.12. Okay, so how many oscillations does the screw experience during its life?
About 2.5.
2.5. So you compare the two oscillations?
As you can see, over here. We basically for the cork boards we compare this set of oscillations. However, for the wood board we used a slightly larger one because we found that the number of oscillations was simply not enough. For the wood one, it was about like 3 to 4 meters. We have a setup of that if you would like to look at it.
Okay, please.
Just over here.
Okay, so how can you make sure that your board is flat?
We basically could just use a level to make sure that the board was flat in relation to this axis. Additionally, we use additional support stand here to ensure that there was no flexing of the board, because with this longer board with such a thin radius, if you prop it up directly, there is buckling, but if you add additional supports, there's no buckling.
Okay. So then can you turn to page 12? So you mentioned that you can control the mass and the length of the screw at the same time. Is that it?
We basically had to compare both of them at the same time because we use different types of screws. Over here we use machine screws. I understand there are other types of screws, but with machine screws, when you change the length, there's like this additional section. If we were to change the if we would have to change the length and not the mass of the screw, we'd probably have to use a different type of screw, which either had a different density of metal or a different radius of the inner and outer points, which simply wasn't reasonable because screws are manufactured for usage and they don't really be consistent with other types of screws.
So how can you make sure that the cause of increase of oscillations is due to length or mass if you have two parameters at one time?
We found with the length of the screw, it was mainly because the period changed. For the mass of the screw, it was more of the difference in forces. We ensured that this was because of length, because the mass of the screw and the length of the screw no, you were right. We were not able to ensure that the length of the mass do not have correlations. However, based on different equations, the length of the screw is normally corresponding to period, and then the mass of the screw is usually corresponding to the mass of the inertia.
So you think that about the period and oscillations, another one can be ignored. Is that it?
Could you restate your phrase? It wasn't very good.
So like if you are talking about the periods, then one parameters will only be changed because the other one can be ignored.
Yes, I believe so. I believe that the mass does not have a significant effect on the period.
Okay. I'm giving you a suggestion to please move the board. So like you mentioned, yes, you mentioned that you can use a cone to explain the oscillations like this. Like this.
Yeah.
Yeah. Okay, I know slightly. And you can just simply, if you can find two plastic plates or a CD, then you can actually put one over here, a smaller one over here, and connect it with something. Then you can control the mass or the length.
Wouldn't that affect the moment of inertia though, if we were to do that? Additionally, wouldn't that affect spreading the screws effect on the moment of inertia? So basically by doing this, wouldn't you be varying a lot more factors than if you were to simply vary the strength of the screw? Such as the concentricity of this, since when you create this yourself, you're not sure that this axis is not in the exact center of rotation. Additionally, there's no threads, which could affect the moment of inertia of the screw itself.
Actually, you can make the hole very small. You can use CDs, or there are something like plastic plates, or you can say Lego. There is some kind of board like this, and it has like a dot in the middle. Then you can contact it, then I'm sure that this axis will actually be at the center. Well, it's just a suggestion. Yeah.
And then, wait, but then how would you calculate the spreading effect of the moment of inertia? So notice how, in order for it to be a screw, it's not simply the head. The definition of the screw is that it's a sort of nail with threads on it in order to be screwed into the cord. The threads themselves are not, I guess you could say they're kind of like a cylinder, but at the same time, the mass is different because the threads have empty space in between, which would have to account for a moment of inertia. By varying these two types of things, you wouldn't be able to model the moment of inertia with the screw in the experiments. Or would you say like doing separate experiments would be
Yes.
the way?
That.
Oh, okay. So
and
you
I
basically
know about your, yeah.
Okay, so yes, I agree that by using this experiment to solely model the length of the screw, that might have been a better way to capture the period.
Okay, thank you. And maybe next question. So actually, friction is a very important point in this experiment. So how do you think friction affects the results?
Oh, I believe that friction affects the conversion rate between the rolling of the screw to the pendulum action of the screw. So by having higher friction, it increases the rate at which the oscillations grow. However, it also affects the rate at which the dampening effect occurs, which means there's a higher chance of it stopping.
Okay. Like you said, it will experience a damping when it is about to stop.
Yeah.
Yes. Then how can you make sure that the screw isn't damping? Like I
The
mean,
screw is always there.
yeah. So how can you make sure that it doesn't affect the results if it's damping?
We cover that with the friction coefficient term of the loss of energy, since the reason for damping is the friction.
Okay. And so you mentioned that friction is like it's an important point in this experiment. So what would happen if this is an ideal model and friction can be ignored on board?
It would not. I do not believe that the screw would oscillate as it went downwards because the screw would not roll, and in turn not rolling would make sure that it would not create the pendulum motion.
Okay. And so the next question, does the screw's period change during its oscillation?
Yeah, the screw changes later on during the oscillations. We were not able to model this exact change in period accurately. However, using the period formula that we had before, this period, this one. Okay, so basically using the period formula, it would be able to do it for different points of time. However, you probably have to factor in more friction.
And so now let's talk about your errors. So you would think that with 25% error, it is considerable. Like, I mean, your period has 25% error. And
Yeah, I
it's
believe
like-
it is considerable. However, we could factor that due to the difference in inertia calculations. Yeah. Yeah.
Can you explain your equation in detail, like the one on page 19 and 20?
Are you talking about the energy formula, or are you talking about the radius arc, or?
The radius one.
Oh, so the radius
I
arc.
think I don't have the.
Okay. So, if you look over here, when the screw, you have two different diameters, right? Well, when the screw rolls, it creates the arcing motion. Like I said, besides the cone, you can also consider it kind of the different velocities of the rolling motion since it's a rigid body, creates this arc, and then comes across this point, right? Well, if you were to extend that point, so that this was one circle, and sorry, the circles are bad. This was another circle, we were able to say that this over here, this is the radius of the outer circle, and this is the radius of the inner circle, right? So the radius of the outer circle is equivalent to R1 plus the length of the screw. Additionally, because the rolling of the screw creates the circle, we know that the circumference of this entire length is equivalent to some multiple of this radius over here, or RH. So this radius over here, and this is R inner. So we know that it's equivalent to some multiple of this circumference, 2 pi RH. And then we know that this circumference is equivalent to some multiple of this radius, or say 2 pi r inner. We know that the multiples are the same because this is a rigid body. So with every rotation, it has the same amount. Because this is the circumference, we know that the ratio of the circumferences is equal to the ratio of the radiuses. So we know that r outer is proportional to r inner if you have r. And then we can solve that in order to find the equation
Sorry, like in this picture, you put your screw over here. So
no, sorry.
The contact
That's misleading. The contact point of the screw is here, the point is here at the center.
Okay, then I get it. So can you explain what are the main parameters that affect the screw?
The main parameters are the friction of the board, the length of the screw, which affects the dimensions, the radius of the outer head, the radius of the inner head, the mass of the screw, and I guess the growth and oscillation will also be affected by the incline of the ramp, which we do not have with them.
Time is up.
Thank you.
Please summarize the discussion.
Okay, so first we talked about the error, and in the opponent's opinion, we don't think that with 25% error, the statistics are considerable. And also about the equations, we know that the reporter has a great understanding of the equations, and they have a relationship between their experiment and equations. And third is a setup. Actually, we see an angle on the board, and about what they talked about, they control the angle and don't make it and would affect the results. And the fourth one is friction, which we just talked about, and they said that without friction, then the screw won't experience an oscillation. And the fifth one is the parameters, and about what they just talked about are the mass and the different radius of the two circles on the screw. And that's my conclusion. Thank you.
Question time from the viewer.
Okay, so thank you for your presentation. So both of you have mentioned about friction. So do you only consider the static friction of a board?
No, I believe we would consider both types of frictions. However, for the rolling motion, yes, we would consider the static friction.
So do you show in your formula that you consider the Gauss kinetic friction?
The kinetic friction will be included in the velocity of the translational.
So do you consider it in your formula?
Yes.
So do you know, also it's because it's sliding?
Yeah, it's slipping.
Slipping, okay. So do you think that the kinetic friction is also should be mentioned about in this experimentation?
Yes.
Okay. So you have mentioned about the inertia, right?
Yeah.
So do you think inertia is related to the length of the screw?
I would say yes, because the length of the screw affects the angle of incline the screw has in relation to the board. However, directly, not really.
Why do you think not really?
Oh, because we have with each type of screw, the radius of the outer head and the radius of the inner head are kept constant. If you change the length, that means the incline angle will differ.
Okay. And do you think the inertia is related to the length of the screw?
Yes, but it's not the main.
Oh, it's not the main reason. Okay. And for both of you, do you think the gravity will affect more to the angular velocity than friction?
Yeah, because it's drawing oscillations.
It's during oscillations.
Yes.
Yes. Okay. And can you turn to page 17? Page 17.
Could you state what's based on the
So I think it's about the energy formula that you provided.
Oh,
And I
yeah.
want to ask about the constant that you add in the back of it. I didn't see.
Are you talking about?
The constant.
Oh, this one?
Yeah, the constant.
This
Oh,
one?
wait, no, yeah. What is that?
That's just total distance traveled by the screw because work is due to force times distance. This is the total distance traveled by the screw, and we could track that through just taking into account the difference points and adding up all the distance values.
Okay. And so to the page 27. Okay, so I think the period in here and here is actually coherent to here. So can you tell me what happened?
Oh, are you talking about the
Yeah,
period
yeah.
here? This is because as it oscillates, it grows faster than the angular frequency. So the period will decrease. We didn't take a calculation of this section over here.
So
However, we believe this was
So this actually is quite unstable and not able to quantify it.
I would say near the end, yes, there's significant error because the oscillations would increase your slip.
Okay, the time is up.
Good morning, honorable judges and my partners and my competitors. I'm the reviewer from Team Domain. Today, the topic I'm going to review is problem number 9, oscillating screw. So, according to the problem statement, the reported team's main focus is on what affects the oscillation or growth of the oscillation and how the relevant parameters affect. Next. So, overview for the reporter. His advantage include the clear explanation of analyzing the structure of the screw. And also, he has shown substantial data to prove his theory. And also, he's got the clear derivation of a formula of finding radius of the arc. And he also has calculated the energy loss meticulously. And however, for the suggestion for him, even if the simulation is of accuracy, he still should reassure it in a real experimentation. For example, like the experiments that he conducted by the Python. And also, he has mentioned about the stop and the slip, but he didn't investigate deep into the conditions that cause it. And also, I asked about if the kinetic friction is taken into account, and he mentioned yes. But however, the thing that he failed to do it like very clearly mentioned in his presentation. And the overview of the opponent, her advantage include good imposing manner, and she also found out detailed mistakes of the reporter, for example, like the parameters. And also she asked about thoughtful questions. And a suggestion for her include she could probably have organized the questions better in terms of the order of the questions. So discussion 1, the opponent asked if the reporter can ensure the oscillating is caused by the damp. If you change two parameters at a time, the reporter says that not able to be sure. And the opponent keep asked if the mass will affect. The reporter responded, no, the mass wouldn't affect. And the opponent keeps if the reporter can use another system that resembles the cylinder that he just used. And the reporter mentioned he don't think so, because it won't be able to model the inertia if you use another system. And she also says that, how do you think the friction will affect? And the reporter thinks the friction will affect the pendulum, and so on. And the opponent asks about damping, and reporter responses, the friction is the main reason for the damping. And also, the opponent keeps asking about the error of 25%. Is the data reliable enough? And the reporter says that the problem can be solved by the inertial calculation. And finally, the opponent says would like to know more about the theory explanation because she feels like its derivation is quite hasty. And the reporter said will fit the explanation the formula by demonstrating the graph on the blackboard. And for the last question, she mentioned about the most important parameter, and the reporter thinks is the friction of the site. So for the conclusion, the reviewer thinks that the reporter should mention the kinetic friction and the static friction respectively and clearly in his presentation. And also, I also asked about the period when the slide is close to the end. And his team says that it's kind of hard to quantify, but I think it should be probably have some relation to the first stable status. So we think that he should also consider it in the presentation. This is the end of this speech. Thank you for listening.
Okay. The concluding remark.
Okay, so first of all, we'd like to say that in our experiments, the length of the screw usually affects the period, and the mass usually affects the moment of inertia. If we were just looking at period, we stated that mass would not significantly affect. Yes, there would be effect, but we think that the relationship could still be based off the length of the screw. We would like to confirm that we checked the board's flatness using a bevel. Additionally, using two plates and a connector would affect even more parameters that would not fit the definition of a screw, but trying the experiment could be advisable if we were trying to figure out relation between length and period. We included damping in our theoretical equation, so it is accounted for by using our loss of energy due to work. The screw period changes during oscillation, which we accounted for. The difference of radius is in the part. Length would affect the moment of the inertia of the pendulum motion, but not when it's rotating on its own axis. Sorry, I thought the reviewer was talking about only the rotating action. However, they were talking about both moments of inertia. And yes, the length would affect the radius from the moment of inertia when it's from the pivot point and it's rotating around. But it would not affect it when it's rolling around its own cone. We talked about why the screw stops at a certain point. It's essentially because of a combination of the period increase along with the incline of the angle. It was shown in our length experiments. We talked about that mass would affect the motion because it would affect gravitational force and moment of inertia slightly. And the friction increased the rate of oscillation in damping. We considered both the kinetic and static friction in our velocity terms. We accounted for the 25% error in our period by taking into account that we did not include the constant for inertia properly. Thank you.
Okay. So the question time for the jury. So Professor Meng.
I have two questions for the reporter. The first one, I may have missed your argument in your report.
Oh.
Why is the amplitude increases? Why does the amplitude of the oscillation increase?
Oh, basically because the potential energy is mainly converted into this rotational energy.
Yes.
And additionally, any potential energy converted into the rolling energy is also converted into pendulum, the kinetic energy of the pendulum, because when it rolls, different velocity changes it into an arcing motion. So both kinetic energies convert into this increase.
But why the amplitude keeps increasing?
Oh,
You said it's oscillating, but
yeah.
the amplitude is increasing. Why is it increasing?
Oh, because the energy in the rotational is increasing. And then it wouldn't.
Yes, I agree, but why?
Why? When it slips, it goes into that, and then there's little to no kinetic energy transfer between it. Also, you could state that
Okay. My second question is, when you see the oscillation of the screw momentarily stops,
yeah.
why does it stop?
Oh, when it like stops in the middle of the board.
Yes.
Because
the maximum reach the maximum amplitude. The screw
when
stops
it reaches the
momentarily.
maximum amplitude.
Why?
Because the rotational energy is converted back into the potential energy.
Yeah, I agree. But
Because there's different amplitudes, right? But it all contains the potential energy from the initial drop of the screw. But when it slips down at different amplitudes. So at different amplitudes, it has differing levels of energy accounted for.
I totally agree with your argument because it's about energy transformation.
Yeah.
But my question is why you have this energy transformation? Because then goes into
Gravity pushes it down. When it comes back up to a certain point, gravity pushes it back down again. The different point is affected by the velocity.
You had this explanation why it stops.
Okay. So maybe we give the chance to the other two.
Wait, are you talking about the two contact points? And then
Shortly answer and then close this discussion and then move to the next jury. So do you want to answer? No.
The experimental data.
Are you talking about the observation or the graph at the end?
The oscillation.
The oscillation, okay.
The oscillation is one.
Or the
You calculate this one.
Oh, this one, okay.
I think here is a regular oscillation. 1, 2, 3, 4, 5. Okay, this is I think it is regular. So what's the? I don't know why. Maybe you you can give some explanation.
I think it can be accounted for because as it's slipping, there's an increasing error between our theory and the oscillations, and then this affects the regularity of the oscillations. Additionally, as it goes down the board, there is less potential energy being, there's a loss of energy which affects the regularity of the oscillations.
So I think, first of all, just like you mentioned, it's related to the energy loss, but also I think the gravity will also have an impact on the torque, and the torque will also impact its angular velocity. So I think that's why it changes like so rapidly.
And friction energy loss converts. Potential energy converts to the friction. Potential energy will turn into friction, and friction will become the energy loss. So it will experience this.
Okay. So is there any short question?
Can you explain the difference between rolling motion and the rotation?
So the rotation motion is when the screw rotates along its own axis, and then the rotational motion or the growth and oscillations is that difference in velocity creating this arcing motion of the.
Okay. Thank you. So the scoring time. Yeah, so the score for the reporter. 88787. The score for the opponent. 78786. The score for the reviewer. 88776. Yeah, so let's close this session.
是你帮他，不是我帮他。这个好，这个对。他把我这个我都给他前面写了。
因为所以我们现在可以讨论的题目是剩下这4个人的，6个，对，
因为他一开始就是
所以OK，这已经开回来了 ，OK， 这样，所以现在6个，
是右边那6个，
已经解开了，对。
OK， 好。
对，因为本来还没解开嘛，对，但题目太少就会解。Okay. Yeah. So the opponent please challenge the question to the reporter.
Wait a minute. Want to challenge question number 15, pancake rotation.
Question number 13.
15, sorry.
15. 15.
We accept, yes.
15. Pancake rotation. Is
Have
it?
like
Okay.
done everything.
We accept the challenge.
Pancake rotation. Problem 15.
它上面好像写着他们
你要把整个页面重新刷新。
这里请说。
我知道，哦，对了，谢谢你哦。
刚刚那个15不要打错了。15。是刚刚选错了吗？
因为他们说13，所以我觉得
是，我也听。
accept 吗
Accepted. 15. You can start.
Dear judges, honors, viewers, I'm a reporter from the team Newgate. And today I'm reporting problem number 15, pancake rotation. So here's the problem statement. If we just place a few bolts in a round container, and if you move the container around a vertical axis, the bolts can move co-directionally with the movement of the container, or they can move in the opposite direction. So we want to investigate the phenomenon, and the direction of movement depends on the gravity. So here's our observation. So we put a few bolts with a few bolts will rotate in the same direction as the container. However, if we put a lot of bolts, they will counter-rotate in the container. And here's our outline. First, we'll introduce our theory, and we'll show you our experiment result, and next is the discussion, and last is the conclusion. So here's our theory. So when the container is rotated, the bolts experience a centrifugal force that pushes them toward the walls of the container. And the magnitude of this force is proportional to the distance of the bolts from the center of rotation. And therefore, for the given rotation velocity, increasing the size of the container will increase the distance of the bolts from the center of rotation, and therefore the magnitude of the centrifugal force experienced by the bolts. And we put some bolts in a circular container and rotate the container around the axis. Since the number of bolts in the container is small, the particle shows the properties of liquid, which has small friction, and the bolts inside will follow the container. On the contrary, add more bolts, the sphere behaves solid quantities, which has high friction, and the bolts will move in the opposite direction. So here's our experimental setup. So the container we use is Petri dish, and the bolts and the particles inside we use beads with one mark for us to track the movement. And the whole movement is conducted by the orbital shaker. And this is our first experiment. So we added the number of beads inside the container and fixed the container's radius, the bead radius, and the rotation velocity. So we found that when the beads in the container is larger than 70, the beads counter-rotate. And next, we change the radius of the container. And the container is the container's radius is 3.5 centimeters and 4.5 centimeters respectively. And a small container where the number of the beads is larger than 60, the beads counter-rotate. And on the other hand, in the large container where the number of the beads is larger than 70, the beads counter-rotate. And next, we change the radius of beads. The radius is 2 millimeters,
small bead, which is 2 millimeters. When the number of the beads is larger than 100, the beads counter-rotate. As for the medium bead, when the number of the beads is larger than 70, the beads counter-rotate. And for the large bead, remember, when the number of the beads is larger than 35, the beads counter-rotate. So here's our discussion. By increasing the number of the balls in the container, we can find a critical value of the start of the counter-rotation. And in a smaller container with the same balls within, the critical values decrease. And in the same radius of container for the small balls, the critical value decrease. And as we said in our theory, the more balls represent an object or similar to a solid and less balls resembles a liquid. If we look at the bottom layer of both the solid and liquid simulations, we see that a solid has more molecules touching the bottom of the container. Since every molecule has the same friction given by the bottom of the container, more molecules means more total friction. The bottom of the container is a friction that goes in with the direction opposite the rotation. So when this friction is able to overcome the friction making the molecules move co-directionally, which is from the size of the container, the whole object as a whole moves in the opposite direction. So here's our conclusion. The movement of the balls in the container depends on many parameters. First is the size of the balls. Based on the theory, the small balls experience a weaker centrifugal force. And the other is the size of the container. By increasing the distance of the balls from the center of rotation, and therefore the magnitude of the centrifugal force experienced by the balls. And this is the end of our presentation.
Okay, so then the question time for the opponent to the reporter.
Please show me your experiment setup. And I can just ask, are you in a non-inertial frame of reference or are you in an inertial frame of reference? Your camera.
We are in
Inertia, okay. And do you know that the centrifugal force is a fictitious force?
Yes.
About your theory, do you have any formula to support your theory? Do you have any formula to support your theory?
No.
And how do you define, like in your theory, you said it's what, like liquid or like solid? And how do you define something in between? How do you define that?
We said that is similar to the movement of liquid in the container rotation and solid rotating in the container.
So you don't have a like concrete boundary in between?
It's on a scale and
okay, it's okay. What about the ball material that you use? Did you use always use the same ball material?
and this in our first section
Okay, the time is up. Okay, the opponent, please start. Take the floor.
Good morning, esteemed judges and fellow debaters. My name is Jerry Gao, and I will be opposing for this question, question 15, pancake rotation. So the problem statement was, place a few balls in a round container. If you move the container around a vertical axis, the ball can move co-directionally with the movement of the container, or they can move in the opposite direction. Explain this phenomenon and investigate how the direction of movement depends on relevant parameters. And they focus on the parameters that and the cause of its change the rotation. About the theory, they had they thought the centrifugal force would affect a lot, and then the increase of size of the container will increase the distance between the balls and the walls, and then the number of balls may be seen as molecules, so have the liquid, like liquid or like solid. And their setup was the container, the petri dishes, the balls, and the orbit shaker. And their parameters, what they changed was the number of beads added, the radius of the beads, and the radius of the container. And the analysis part, the counter rotation starts when friction from the bottom overcomes with the friction from side, and the relation between parameters and and the rotation direction. And their conclusion was the movement of balls depends on the size of the ball, And the movement of ball depends on the size of the container as well. Which would be something I would want to make more concrete on our discussion. And their advantages was they had massive data for each experiment. And our suggestions was that they probably could have more parameters. And they probably should have shown some formula to support their hypothesis. And they didn't have like quantified numerical results. And their demonstrations of graphs aren't clear enough. And the meaning, so we will be discussing the meaning of the three experiments respectively, and possible more concrete conclusion, and the theory and the discussion of the possible force diagram that they did not show, and the material and the coefficient of friction, and the other conditions that should be controlled better, and suggestions for other parameters that should be included. Okay, and that would be it, and I would like to start my questions. And page 8. Can you explain the X and Y thing? Because I don't really get your graph.
It is the movement of the waffle and the X and Y axis.
So this is how you got your rotation velocity?
We didn't calculate it.
Oh, so you calculated it. But if you notice, then the unit is actually wrong because the velocity should be radius divided by seconds or something, or degrees divided by seconds. But this is centimeters by seconds. So I believe that maybe you should use another, if you want the rotation velocity, I suggest you that you can use trace the theta that's rotating around the, trace the theta of the law that's rotating around the container, and then you divided it by time and you get the real omega that's supposedly the unit will be correct. And then can you briefly explain your second theory? Your theory part. What friction? The small friction and high friction, what does that mean?
And the friction between the balls.
Okay. And right now, I'm going to, based on their experiments, because we respect their experiments, so we will be wanting to make more concrete conclusions based on their experiments. So, what do you tell me what you were trying to find in your first experiment?
We want to find the control value of when the rotation and how does the how much friction at the bottom needed to be to overcome the friction of the ball and
So, in other words, fit it back to your theory over here. You're trying to define, like, in which conditions can your balls be seen, like the molecules be more seen like a liquid state or a solid state. Am I correct? This might be your real meaning of this term. You're trying to define a boundary.
Because it's like the spectrum, more like a solid, move like the solid, and the outside is move like the liquid. So it's not the definitely show the liquid or solid.
But in your theory, you think that when it can be seen as a solid state, then it will move in the opposite direction. So what causes counter-rotation, according to your theory, is that it can be seen as a more solid state. Am I correct? So you're trying to find the boundary in between.
Not quite the boundary, but here is liquid and I think we talk about liquid and solid. Just want to
So what causes counter rotation? It's because, according to your theory, it's because it can't be seen in a more solid state. Do you agree?
Yes.
Yes. Okay, now in your second experiment, what do you want? What are you really trying to find?
We want to find the we want to see how the radius of the continuous affect the result.
Yes, exactly. Which and fits back to the theory. You're actually trying to find the same thing, which is the boundary in between. Now in your third experiment, what are you trying to find?
Oh, we want to find how the different radius of these affect the result. And
Yes, which is basically meaning that they wanted to find the same thing. Like, you wanted to find the boundary in between. Now, what do you think this boundary may be affected? Like, how? Since you change different radius, then what do you think will affect?
the spectrum between the walls and the wall and the walls and the well trend.
Well, is there a possibility that in a certain mass ratio, then it can be seen as, in your theory, a more solid state?
I think this can affect the density.
The density, yeah, and maybe you can use the area ratio to define as it's more liquid or it's like more solid in your theory, according to your theory. Because all my discussions, we are talking about your experience, so we would like to discuss all your experience results.
Yes, I think I would go back in your terminals and review this.
Okay, then may you draw a force diagram of the balls.
So it's weird that now inertia and we think of we view our balls as an object, and so here's the center of the balls, and this is the center of the package. And we can point out one more here, and they will. Here's it, centripetal force. And here.
Normal force? Normal force or centrifugal force? Centrifugal force means that other force. Oh, okay, I get you.
And the word will give this object friction.
Friction, yes, friction. Now, if you look back into your inner theory, you think that friction will be a very important parameter. But as the short questions that I said to you, I asked you that you didn't use the same ball material, which this changes the coefficient of friction, which makes your experiments like not so accurate. So if you look back in your second experiment.
And this experiment, we're not discussing the same.
Yes, I'm trying to tell you something. You see that, and you're using the when the large container is 90, the radius is 4.5 centimeters, and your ball beads are 0.3. You would need 70 balls. You would need 70 balls to cause conservation. But in your third experiment, like this is 4.5, and your little walls are 0.8. And in your third experiment, you did the same thing, but you changed the little ball into 0.4. But you still needed to put 70 balls. 70 balls. So there might be something in between that changes.
Yes, but to find that as here, the small growth is and the larger growth is not the same material.
Yes. So what changes when you change different material? The coefficient of friction. So the coefficient of friction will also matter. Then which do you think will matter more? When your coefficient of friction is bigger, then do you think it will be easier to counter-rotate or harder to counter-rotate? Easier to counter-rotate. Yes. So this might be some of the problems according to your experiments that you would want to choose and change, because you change different coefficient of friction, then this will probably be one of the things that you will want to see. Yeah.
I want to respond to the earlier question you asked. We are trying to find the boundary of counter-rotation, not the boundary of solid and liquid.
Yes, but what causes counter-rotation is the boundaries of your solid and liquid thing, right? Because according to your theory, then that would be contradictory if you're thinking that I'm wrong, because all my discussion is based on your theory. So you agree with me on that, right?
Yes.
Yes. So we suggest you that maybe according to experiments, you can see this difference already. So maybe you would want to do another set of experiments that include the yeah, we have no time left.
Okay, the time is up. So please summarize the discussion.
We found out that according to their experiments, to make their boundaries more concrete, because their discussion was only like for effects, but how does it affect, and which conditions does it affect? So we thought that maybe the area ratio would be the boundaries of counter-rotation and rotation. And in our own experiments, that's true. So yeah, that would be something that they want to quantify. And one thing is that in their experiments, they change the materials, which changes the coefficient of friction. And we discussed about it, and she thinks that when the coefficient of friction is bigger, it will be easier to counter-rotate, which fits their theory, which we think that is a good discussion.
Okay. So the reviewer, please give you a question.
Okay, so thank you for the reporter and the opponent for the discussion. So first, a question for both. What do you think are the most important parameters that may affect the rotation of the ball? Friction? Okay, and
There are very many parameters to be included, like the angular velocity of the container, and then the coefficient of friction, the ball mass, and then the soling speed, and various things that they did not consider, but yeah.
okay. And since the opponent mentioned that centripetal force is not real force, I want to ask, how would you define the centripetal force for both? So starting with the reporter. Okay, I'm gonna ask you later. What would the opponent say?
It's like when we are in a non-inertial frame of reference, then the centrifugal force would point outside, like of the container. Like if this is the center of the soling, then it will point outside, like here. Okay. Centrifugal force.
Okay. 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 Now, question for the reporter only. Since you mentioned that the balls can be like you use an analogy of the states of mass of the balls. So do you think the balls should be considered like consider it like as a cluster and like analyze the motion of the cluster instead of individual balls in this experiment?
Yes.
Yes. Okay. Also, and for both contestants, how many tons of friction do you think are in this system?
There's mainly the kinetic friction and maybe a little bit change.
I mean like friction like caused by like the bottom of like the container, like stuff like that.
Three times the bottom of the container and the balls at the balls, the friction between the balls and the friction between the balls and the balls.
Okay, and opponent?
If the coefficient of friction is high enough, then there will be static friction. But if the coefficient of friction is not high enough, then there might be kinetic friction.
Okay. Do you think like the interaction between the balls may also affect the motion?
Yes, but in our experiments, we did other things that the change would be small, minor.
Okay. Thank you.
Okay, so it's 2 minutes for the preparation of the reviewer.
Okay.
So please start.
Hello everyone, my name is Ethan Cho from No Letters, and I'll be reviewer for number 15, pancake flotation. So the problem statement is place a few balls in a round container. If you move the container around a vertical axis, the balls can move co-directionally with the movement of the container, or they can move in the opposite direction. Explain the phenomena and investigate how the direction of the movement depends on the relevant parameters. So judging the reporter's performance, they had a good qualitative explanation of trying to correlate it with the states of matter, but they had a short presentation, no quantitative explanation of the phenomenon, and did not account for some parameters, and a struggle to answer the opponent's questions. And also they didn't have access labels for the graphs. And for the opponent, I felt like he asked relevant questions, but he could have managed his time a bit better, and he also brought up their own experiment observations during questioning. Right, so on to the discussion. The first thing, opponent asked the reporter to clarify the graphs, and the reporter said the graphs represent the motion of the x and y axes, and the reviewer thinks that radians should be used, but centimeters should also be used to complement it. Next is a discussion about experiment. The opponent asked the reporter to clarify the experiment, and the reporter said they tested how much friction is at the bottom and that's needed to overcome the side friction, and the reviewer agrees that the cause of change in rotation is the friction between the walls and the bottom, and therefore this should definitely be investigated. And next, the opponent asks about what causes the counter rotation, and the reporter likened the system to states of matter. But the reviewer believes the counter rotation is caused by the friction of the balls and the bottom versus the friction with the walls. Next, the opponent asked about the effects of the radius, and the reporter stated it can affect the density of the system if it's modeled as states of matter. The reviewer believes that instead of looking at different radii of the balls, we should instead look at how much area the balls cover in relation to how big the container actually is, and this would also define. This will be the main factor in the rotation. And next, the opponent asked about how changing materials will affect the coefficient of friction, and the reporter didn't really hear an answer for this. And the reviewer thinks that indeed the material changes the coefficient of friction, and this will also affect the motion. And next, the opponent asked about the movement of the ball inwards. The reporter said it was due to centrifugal force. And then the reviewer thinks although like centrifugal force is a real force, it can be useful to model the system. And other things they discussed is modeling the system as different states of matter and other parameters. And the points missed, I think they didn't really cover the ball's interaction with each other until I questioned them about it. And they also didn't mention the frequency of the rotation, how faster rotation may affect the system. And also they also didn't talk about how changing the axis of rotation of the container may also affect the motion. All right, thank you.
Okay. So, good. So it's the concluding remark for the reporter.
We are trying to find the boundary of communication, not the boundary of solids and liquids. And when we say solids and liquids, it's not a scale that resemble one and more, and it's not definite. And we should have calculated the area in which the balls covered, and we should also fix the materials of our balls. And there are more parameters such as rotating speed and different materials that we can discuss. We should have a formula to support our theories and our experiments. And that's it. Thank you.
Okay. So it's the question time for the jury. So I think that this is a question of classical mechanics. So the force analysis is very important. So I would like to ask from the opponent. So can you show your opinion or just draw a figure on how you analyze the force for this motion?
For this motion, you mean how I analyze it, or the force diagram? So I have to draw the force diagram. One single wall or many balls?
Yeah, just one disc or one ball. Yeah.
One ball, okay. Like, this is the container, and this is the ball. It's like here, because it's gonna get pushed by the centrifugal force. So now there will be gravity that goes inwards. There will be the normal force that goes outwards. And if my container rotation is like this, then the coefficient of the friction will have a displacement force, and then the centrifugal force is pushing it over here, centrifugal force, and then there will be a Coriolis force like 90 degrees Coriolis force, and then there will be friction, normal force between the container of the wall and the normal force container of the wall and the balls, and then there will also be a friction of the container wall.
Okay, good. So for the reviewer, do you want to add something? Or do you want to modify? Yeah.
I think the opponent covered most of the forces that we considered.
Okay. Yeah. So open for the jury.
I have one question to the reporter. Do you think it's easy to write down the formula for your experiment? If not, can you give a reason? If you don't think so, can you give a reason?
I think that there are too many parameters to consider.
Too many parameters. Okay.
So, the other juror, do you have some more further question?
May I forward a question to the opponent as well? The same question.
Can you repeat your question?
Yeah, my question is, do you think whether it's easy to write down a formula?
The actual formula might be hard to calculate, but if you see like the forces in between, then you can probably see how like omega affects the forces and how movements. You can, though it's really hard to find an accurate formula, but you can at least find out if it's negatively correlated or positively correlated.
So, is there any further question? No. Let's go. So, the score for the reporter, 5, 5, 5, 6, 5. Consistent. So, the score for the opponent, 7, 7, 6, 7, 7. The score for the reviewer, 7, 6, 6, 7, 7. Yeah. 好，那我想今天大家的话呢，其实表现的都不错哈，因为这个3天下来，其实大家的这个也越来越进入状况，好，越来越进入状况。好，那我们聚会有没有什么要勉励一下大家的？我想那个其实做物理题目是蛮有趣的啊，那相信大家应该都花了蛮多时间啊。那这个到这个场合里面啊，我想除了这个 present 你的这个结果之外的话，我想跟其他的队伍之间的切磋，其实大家可以学了很多啊。那也希望大家持续的加油啊。另外那个一个小小的建议哈，那个时间还是要注意一下你的 projector 啊，我想。那个这样比较不会影响到这个整体的时间啊。好，那所以还有没有什么要讲？好，那没有我们就。